So far you have learned that given that the y's are given by this functional mapping plus some random noise epsilon, which has a zero mean, the likelihood of the parameter w is equal to the probability of the observations yi given xi, right? So now we are going to make assumptions on the noise epsilon I. So let's assume that this epsilon I has a Gaussian or a normal distribution. So epsilon I has distribution as a normal distribution with mean 0 and variance sigma square. So then the probability distribution function of epsilon is given by 1 over square root of 2 pi times sigma square times xp of negative of epsilon square over 2 sigma square. So this is the definition of a normal distribution. So if we had a mean mu, then this would become epsilon minus mu square. Now since we have assumed that the mean is 0, then this simply becomes epsilon square. Right. So now, as you have seen, that the probability of yi, of the observation yi, given xi and the penetration parameter w is simply the probability of epsilon I, right? Where epsilon I is yi minus fw of phi of xi. So now also assume that in linear regression we have seen that we use the linear models, right? So here also we'll consider the linear models. So let's assume that fw again is phi of x transpose times w. So we're going to assume the linear model over here. So in that particular case, epsilon I becomes yi minus phi of xi transpose times w. So we can now plug this in into this and further over here. So we get the likelihood of the parameter is equal to multiplication of the individual probabilities sigma square times axp, the negative of yi minus phi of xi transpose times w whole square divided by twice of sigma square. So we can further simplify this. Sigma square times exponential of, we can just rewrite this simply as doing this multiplication 1 over 2 pi to the power n by 2 times sigma to the power 2n times exponential of negative of sum of I equal to 1 to n yi minus phi of xi transpose times w over 2 sigma square. So this is the likelihood of the parameter w. So to get the optimal w, we can maximize the likelihood. So we get WMLE, or the maximum likelihood estimate of the parameter W, is the one that maximizes the likelihood, is argmax W L of W. So now, as you can see, this likelihood function is a very complicated function, right? So we can simplify it further by taking log on both sides. And log has very special property that it's a monotonically increasing function. What it means is that if you do the plot of log of x, for some scalar x, is a monotonically increasing function. What does it mean is that if you select a value x2 and a value x1, so for all x, so the monotonically increasing means that log of x1 would be less than log of x2 if x2 is if x2 is greater than x1, or x1 is less than x2, right? So we can take log on both sides. Since it's a monotonically increasing function, we can take a log. So I'll just erase this to give things simpler. So instead of maximizing this, we maximize the log of the likelihood. So log of the likelihood is simply, so we can assume that this is some constant C. So this would be log of the constant C plus log of the exponent of negative of sum I equal to 1 to n yi minus phi of xi transpose times w square over 2 sigma square. So this would simply be log likelihood. We can just simply write LW, which means the log likelihood function. So log likelihood of W is some constant minus sum or I equal to 1 to n yi minus phi of xi transpose times w over 1 over 2 sigma square. So since sigma is independent of this w, right, we can just assume that this is also another constant. So the log likelihood of w is simply some constant, this is again some constant c1 minus c2 times, which is positive, so c2 is positive, I equal to 1 to n yi minus phi of xi transpose times w the square. So since c1 and c2 don't depend on w, so while maximize them, we can just get rid of them since they're differential. So to maximize this function, we differentiate, instead of maximizing this, so since c2 is positive, so this entire term would be negative, right? So instead of maximize the likelihood, we can just minimize the negative of the log likelihood. So maximizing the log likelihood W is same as minimizing the negative of the log likelihood of W. Right. So just take the negative and this would become negative log likelihood of W is some constant alpha plus some constant beta. So since this is positive, so this entire thing would be negative, and the negative of that would be positive, plus some beta times, where beta is some positive, sum all I equal to 1 to m yi minus phi of xi transpose w to whole square. And now to minimize this function, we'll just take its derivative with respect to w and set to 0. So we can just ignore alpha and beta, since once we differentiate, the derivative of this with respect to w would be 0, and like this would become constant. Once we set it to 0, then this just cancels out, right? So we can just write the negative of the log likelihood of w is simply some positive constant beta times sum all I equal to 1 to m yi minus phi of xi transpose times w whole square. So maximizing this means maximizing this term with respect to w. And the previous lectures we have seen how to maximize this term. So this is exactly our L2 norm. So if you remember the earlier lecture, we considered that we had a data set D with m data points yi and xi, where I goes from 1 to m, right? And the loss function was simply sum all I equal to 1 to m. The loss function over the data was simply sum all I equal to 1 to m yi minus phi of xi transpose times w whole square, right? So we now know how to maximize this, both using the closed form solution or using the stochastic gradient descent. So we set complete derivative, set to 0, we get the solution, right? So in summary, what we have learned is that if we have a data is yi is given by phi transpose times phi of xi transpose times w plus some random noise epsilon, and if we assume that this noise is 0 mean and variance sigma square, normal distribution with mean 0 and variance sigma square, that is epsilon is normal with mean 0 and sigma square, and if we assume that the mapping function is linear, then we get the same solution as performing the least squares with respect to the we get the same solution as we get by minimizing the least square error with respect to the parameter w on the data set. That is, whenever we have some data set D, right, yi and xi, and when we select the least square loss function, we are assuming that the noise in the data set has Gaussian distribution, right? So write it compactly for a data set D, xi and yi, where yi is equals to fw of xi plus some noise epsilon I, and if we assume that this has a normal distribution of mean 0 and variance sigma square, some value sigma square, then by maximizing the likelihood of the parameter, the likelihood of the parameter w results in the least square solution. That is, it's equivalent to minimizing this cost function over the dataset with respect to the w. The solution here we obtain is the maximum likelihood estimate by assuming that the noise has the noises have a normal distribution. and we assume a linear mapping function. Whether we use linear mapping or not, it's irrelevant, because ultimately we'll get a solution like yi minus fw of phi of xi square, so I equal to 1 to m. Even if we don't assume a linear model, right? Here also we'll get the same thing. Instead of this phi times, we will plug in the functional mapping. So what it effectively means, if we assume that that the errors have a zero mean and sigma square variance normal distribution, then perform the maximum likelihood. Then the maximum likelihood of the parameters w is same as the one that you obtained by using the least square as a cost function. So that's it for this particular lecture.